Hi guys, we are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are running on all the areas in science, and today we are here with you to continue on chemistry. We are going to look at acids, bases, and salt. This is our first video on acid, base and salt, and we are going to cover Arrhenius concept, Rostellari concept, and Lewis concept of acids and bases. This topic is our acid topic. In our first topic, we look at interatomic bonds, also the same as chemical bond. We covered intermolecular bonds, which is also the same as physical bond. We went to organic chemistry part 1, general concept, and then we also studied organic chemistry part 2, alkanes, and then we did thermochemistry, also called energy changes. This is our acid topic, and we are on acids, bases, and salts. Now, to understand that, you have to know that in the early days of chemistry, chemists were searching and organizing the physical and the chemical properties of substances in the laboratory. Now, they discovered that many substances that we see around, that we use, can be divided into two main categories. That is, one group of substances, they discovered that they have sharp taste or they have sour taste. The other group of substances, they also discovered that they had what? Bitter taste. And they called the sour substances as acids and the bitter substances as what? As bases. And so based on that, substances are generally categorized into two, or chemicals are generally categorized into two, that is acids and what? And base. Based on the fact that the acids have a sharp taste and then the bitter has what? The base has what? A bitter taste. They perform other experiments, and then it's also revealed that this sharp taste substances or sour taste substances always give off hydrogen when added to what? Metals. And again, they also give out what? Carbon dioxide when added with what? Carbonate. But for the base, they were not giving out hydrogen gas when even metals are added to them, but they felt soapy, and when it can also react with what? Fat to give what? A soap. And so they discovered that these substances were of different categories, and that were also of different categories. But to really explain this, many scientists came out and suggested various theories, to enable us understand the behavior of these substances. The first scientist who came out with a comprehensive theory on acids and base was Arrhenius. Now what did Arrhenius say? Arrhenius said that acids are substances that yield excess hydrogen ions in aqueous solution. Acids are substances that yield excess hydrogen ions in aqueous solution. And so we are going to write the Arrhenius concept. So this is the Arrhenius concept. Arrhenius acid. Now these substances, he said, it yield excess H+ ions, that is hydrogen ions, in aqueous solution. And so therefore it means that for his acids, they must contain hydrogen atom. They must contain hydrogen atom. And one example of that is HCl, which contain what? H. And so when you pour H, that is when you pour hydrochloric acid in water, Arrhenius said that for acids, they must give off what? Excess H+ ions in the water. And so I have to indicate the water by writing aqueous over here. And then this come out as negative, call this. That's the chloride ion there. That's the chloride ion there. And so he said that for substances, for a substance to be called an acid, basically what it means is that it gives off excess what? Hydrogen ions in what? In water. It gives off excess hydrogen ions in what? In water. Excess hydrogen ions. Or in aqueous solution. Good. Now, therefore, let me also give another example here. That is A2SO4. That is A2SO4. And so if I add A2SO4, to water, what it means is that the two hydrogen ions that are here are going to drop, so are going to drop, and then they will be released into the water as this, and then we will have what we call the sulfate ion also coming out as that. Remember that they are all in what? In water. So therefore you have to describe them by that, by aqueous. They are all in water. So these are the two examples that we can give. So quickly, if you want to give more examples of acids, it means that these acids must have hydrogen ions, okay, as the main element. And so we have other examples, and I have given you one already as hydrochloric acid, which contain the H, and then we have the A2SO4, which also contain the H. We also have hydrogen nitrate, okay. We also have the hydrogen nitrate. We also have what we call the hydrogen what? Carbonate. These are all examples of what? Of Arrhenius what? Acids. And because why? They contain the H, they have the H here, they have the H, they have the H, they have the H. These are the acids that when dissolved in water, okay, these are the acids that when dissolved in water produce excess H plus ion in what? In aqueous solution, or produce excess what? H plus ion in what? In the water. Very simple. Now let's go to Arrhenius what? Base. The Arrhenius base is saying that for Arrhenius base, there are substances that yield hydroxide ion in what? In aqueous solution, or there are substances that yield excess hydroxide ion in what? In aqueous solution. Now the excess is very important because already there are some ions in water, which is the H plus ion and then the OH, okay, minus in water. Already there are some hydrogen ions and the hydroxide ions already existing in water. In every water that we fetch, there are some ions there, H plus ions and the OH minus. Okay, they are there. But okay, for Arrhenius acid to be called acid, they must give off more of these H plus ions in the water. And for Arrhenius base to be called base, they must give off more what? Hydroxide ion in what? In water. And so for hydroxide, examples of the bases, okay, let me give you examples of the bases. For the bases, it says that they must have hydroxide. So as the main element, they must have hydroxide. They must have the hydroxide. They must have the hydroxide. And so quickly, let me give an example. I have sodium hydroxide. I have the sodium hydroxide. And when sodium hydroxide is dissolved in water, what do I have? I have the sodium plus and then the what? The hydroxide ion. This is the main one we are talking about, the hydroxide. And so this is what is causing the bitter taste. If this is in excess in water, this is what is actually causing the bitter taste. Okay, now that is example. Remember that these are in aqueous solution, so AQ should be written under. AQ should be written under. Other examples we can write is potassium hydroxide. The other examples are potassium hydroxide, and when I add it to water, which is under here, the potassium plus is going to split, and then we are going to get excess what? H plus ion in water. Remember that the water already has what? Hydroxide ion, okay? But for base, they produce more of the OH what? Ions in the water, or the hydroxide ions in the water, making it what? Bitter, making the water bitter. So it is out of the excess OH ions in the water that makes it what? Bitter. So these are examples. We can write more examples of that. I can also have lithium what? Hydroxide. And when I dissolve lithium hydroxide in water, okay, the lithium is going to what? To separate from the hydroxide. The lithium ion is going to separate from the hydroxide. And so I have what we call that over there. Remember that these metals I have taken are all group 1 metals. This metal is a group 1 metal, that is a group 1 metal. They have only 1 electrons on their last shell. And so therefore they have plus 1 plus 1 plus 1. So that is why I'm writing the plus 1. And so I have this one, and also in what? In water. Other examples we can take are the group 2 metals. Okay, that is the calcium. Okay, the calcium hydroxide. For the group 2, they have 2 valence electrons, and so therefore the informing compound, they cross their valences. Okay, and so when I add this one to water, what it means is that the calcium is going to break out to form the calcium 2 plus, and then the OH will come into the water, making it excess. Because already I said that there is already OH in the water. Okay, the water also has its own ions. Every water that we fetch has its own ions, but for base they give off excess of the OH ions in the water, and so making what we call what the whole thing what bitter. Okay, making what we call the whole thing bitter. Now the other example we can write is another one, group 2 metals. This one, the OH, that is magnesium, is also in group 2, and when you dissolve it in water, we are going to get that. Remember to write the aqueous under, and then we are also going to get this over there. But when, okay, here we have 2 of the OH, here there's 2 of the OH, so therefore I have to put the 2 over here to make sure that it is balanced. OH, we have the aqueous, and here to have to put the 2 over here, because remember that here is what is 2, and so I have to put 2 over there. So we have that one. Now, but again, I will tell you that Arrhenius faced a limitation. Okay, his concept of acid and base was limited, and so based on this limitation, other scientists also worked around that, and then we came out with more open more open theory that help us to understand larger group of of substances. And so the limitation was that Arrhenius' limitation was that he limited the acids to only hydrogen containing compounds. It means that only acid or only compounds that contain hydrogen can act as an acid, and which is not so, because there are also other substances that we have discovered that were not containing hydrogens, or that do not contain hydrogen but still act as as acids. And so there are more explanation to this. Okay, there are more explanation to this, and so there is a limitation to Arrhenius' concept, that he limited his acid to hydrogen containing substances, which is limited. Now the other limitation is that he limited his concept or his reaction to only in water. Okay, so he said that for only in water that do we have the acids occurring. For only in water do we have the acid occurring, and this is also a problem, that the solvent he used was water, and so the definition was limited to water. The reaction was limited to water, and so therefore it is not. There are also other solvents that we have also seen that acid is behaving the same manner also inside. Now we'll end our lecture here, and in our next lecture we'll be looking at a broader concept, and where we are going to help solve this limitation. We are going to look at the Brostolori concept of acids and base. Thank you.